Yeah, good morning. Welcome to the second part here. As I said outside, unfortunately, this is something I cannot do on the beach because I will talk about numerical stuff and numerical methods. And I can assure you, you cannot do numerics on the beach because I was on a conference 2 weeks ago and we were on a beach and now my laptop is dead because it got some sand inside. So don't take your laptop to the beach, so I have to take an older one, but it's still fine. Okay, so as I said, the idea of this is I want to talk a little bit about the numerical side of theory research. But as common, I will just start by a sort of general introduction and the motivation and why we're actually doing this. So just first to introduce myself, I didn't put my name, just my last name is here, Johannes Schachenmayer. I'm a CNS researcher in Strasbourg at our new shiny center, which we call the European Center for Quantum Sciences. And it's a big fancy name. It doesn't mean that we claim we are the European Center for Quantum Physics, but it's just because Strasbourg is pretty much in the geographic center of Europe. At least it was before the UK exited. Now it's a bit shifted, I think. But so we are right here. It's a beautiful place. We have a beautiful new building. So if you come by, let me know. Okay, so the first general introduction, so why I want to do numerics in a quantum many-body system. And let me call it kind of like a fancy word, but let me call it the many-body quantum frontier. So what I'm really interested in is thinking about sort of what can you do with kind of macroscopic coherent quantum states on a big Hilbert space. Because if you think about sort of the normal regime where quantum physics happens, it typically happens on the microscopic world, where you have single atoms, you have quantum effects, you have entangled states of electrons and things like that. But then if you make the system bigger and bigger, there's usually something that makes this, destroys this quantum effects, and you go to a macroscopic world, which you can pretty well describe with sort of classical physics. Except for some very rare cases where we know that we have some type of macroscopic scale quantum effects happening, for example, superfluidity or superconductivity. So the way that I like to think about this is really that if you go to a quantum many-body system, sorry, this is a bit contrast not so good. So you have this huge many-body Hilbert space. Right? It's really gigantic because it blows up exponentially with the number of particles that you have in your system. But then in reality, of course, you have always some noise, you have some disorder, or you have some limited interaction range of your systems. So and that type of makes your physics more classical, so it means that it happens typically on a much smaller size of the Hilbert space. And even sort of exotic effects like superconductivity, I mean, we have very good theories for that, which are just based on like two-body correlations. So even those effects, they typically happen on a very small subfractions. So the question is now, okay, what if you have some experimental possibility to create these much, much larger superpositions? What type of physics can you find there? What is out there? And I really like to think about this as a frontier, if you like, because if you think about physics, it always has been driven by frontiers. And nowadays we have sort of high energy physics where you smash particles at like crazy energies, but it's kind of at a limit. And you try to go to higher energies. And in a similar way, I think we should try to go to sort of larger and larger macroscopic clean superpositions. And I think that's really a main motivation for quantum computing and why we want to build these machines, because you can explore what is kind of out there. And there are really interesting questions out there. So I think for me, the most interesting one is actually, does quantum physics hold on this macroscopic scale? Because nobody has really shown this. I mean, there's like theories about quantum error correction in quantum computers that in principle allows you to go out there, but nobody has demonstrated it experimentally. So maybe actually quantum physics fails at a certain scale, and this is a fundamental cool question. But then of course there are practical motivations to go there, sort of just engineering materials, bringing superconductivity to room temperature, and of course computing, factoring numbers and things like that. Okay, and the exciting thing is sort of, this is my background. I come from this cold atom physics field. So in the last sort of few decades, there have really been new experimental platforms with optical lattices or tweezers, or all type of systems like trapped ions, or if you like, really any quantum computing platform out there that are really pushing into this regime. They can do cleaner and cleaner quantum operations and quantum gates. So experimentally, we are approaching the regime where we are getting there, where things may get really interesting. But what I want to do is, I tell you, I want to solve this numerically. So I want to solve this problem on a classical computer. So here's just the problem that I will talk about in this whole lecture. It's just really this is non-equilibrium physics, so we talk about situations where we have some type of initial state, which is still relatively simple, in a many-body system, and then we ask how does this state evolve as a function of time. Ideally, if I have no decoherence at all, if I have just Hamiltonian dynamics, but of course in reality there's always some small type of noise happening, so I will also talk about how to do time evolution in noisy models where you have your system described by a density matrix and you have some type of noise processes in the system. And as I said, what I want to do is just to motivate really classical simulations of this, because so nowadays there are these gigantic claims out there in terms of quantum computers, right? So because even if you take your simplest spin model, so you have a bunch of two-level systems, and you just think about the size of the Hilbert space is 2 to the m. So if you take like 300 of these type of two-level atoms, then you would need down, if you want to write down this state in a classical computer memory, you need something like 10 to the 82 gigabyte, and of course this is never going to be possible, even if you collect all of the atoms in the universe. And you hear quite often this is an argument for like quantum computing to actually use that space. But again, I want to be more cautious about this because, as I explained to you before, actually the real physics is not really usually taking place on this huge Hilbert space. Right? The real physics in our world is on a very tiny subfraction because there's no macroscopic quantum tunneling happening all the time and things like that. And I really like the idea of using sort of numerical simulations on a classical computer to really understand this kind of complexity more better. Right? Because on the one hand, sort of our world is always a bit classical, so we should also be able to numerically simulate it on a classical computer better. And that's one main motivation. So what I do, I take this problem that we have, and I want to put it on a classical hardware. Okay, motivation for this is, of course, model experiments. That's the official motivation sometimes. But of course, also like the interest in sort of just really benchmarking sort of quantum computing platforms, because there have been all these claims out there about that you have already quantum computers that are useful. I would say not really, but sort of classical simulations are really the pragmatic approach to tell you when you have this quantum advantage. You can find new emergent macroscopic phenomena. And really, I like most really just to understand sort of quantum many-body systems from a classical computational complexity perspective. Okay, so that's sort of the main motivation. So what I want to do in this 3 courses, again, I really don't have also too much time. So I want to just bring you a little bit sort of into the world of sort of classical techniques to numerically simulate a quantum systems. So also, as Jean-Sébastien already said before, this is kind of a lecture that's not going to go into the extreme detail of small things, but I really just want to give you a bit of an overview, a starting point to start looking closer. Okay, so 3 lectures. So first I want to talk a little bit about fundamental foundations. So how do you deal with standard many-body quantum mechanics on a computer? And I want to introduce some standard numerical techniques and why they work. And talk about some application to an ultra-cold bosonic system. Also so this is all today, and the first 2 lectures I will talk about numerical methods that allow you to deal with relatively small many-body systems. So we will all stay into the limit of below 30 spins, if you like. But then I think the really cool thing is going to be in the 3rd lecture, and I want to bring you to that point, to also show you techniques that you can simulate these 300 spins that I was talking about before that seems to be unsimulatable. I will show you some techniques that you can very well simulate this on a classical computer. Okay, so I don't follow any book or so. I just put some classical book out there that's also available online. And kind of the philosophy that I want to do is this kind of, so this is not a tutorial on how to compute things, but if I want to give you sort of some examples, I'm also going to show some code examples. I'm not going to give you any code or anything because I see nowadays what happens if you do sort of numerical physics, then people get these notebooks and then they just click through it and you don't understand anything. So I really encourage to kind of like write little code pieces yourself sometimes. And so here I show examples we use now in our group mostly this programming language. It's called Julia. It's open source. It's easily available and it has fast linear algebra and it's really easy to write code. in that. So I will show examples that are written in this type of language, and I encourage you to kind of reproduce these type of things. It's really simple. And you can really do amazing physics, even amazingly sounding complicated physics with just a few lines of code, actually. Okay, so sometimes it's good to explain an idea of a lecture just by telling what it's not. So it's certainly not a complete lecture, so there are many techniques that I will not talk about. I will not talk about Monte Carlo methods, I will not talk about fermions or phase-based methods. There are many other techniques out there that I ignore. Also, it's definitely not a computer science class, so I will not do any complexity proofs or anything like that. And as I just said, it's really not a numerical tutorial. I will just show you code examples to kind of prove that things are really simple to do. And it should be an incentive for you to do it yourself. All right, so that was just to set the stage. So I wanted to get started. Yeah, just to get this out of the way. H bar is always going to be 1, just simply, you will see for numerical purpose, it just makes total sense. It would be crazy to deal with H bar style numbers. And okay, so this is the plan that I want to do today. So I have 4 parts. I think it may be a bit ambitious. If I run out of time, I prefer to rather stop earlier and just shift things to the next lecture than just racing through it. So if I'm too fast, please stop me. Also because I do the lectures on slides, it's always the danger that one goes too quickly. So I encourage you to really ask any questions at any time. So in the first part, I want to talk a little bit about sort of computer science aspect and the question about how we actually represent numbers in a classical memory. This is going to be very quickly. More important of this, I want to talk more about just the simple linear algebra, about quantum mechanics, or just diagonalization, just numerically how you do it. Then in the second part, I want to just talk a little bit about the Gross-Petersky equation, just briefly derive it, sort of in general mean field approximations, which make the system always classical by definition, but which also allow you to do a lot of calculations also in very large systems. Then I want to go to sort of a very simple numerical method to integrate those type of methods. And in the end, if you have time, I want to show you some movies of how dynamics happens in these systems. Okay, just again, no computer science class, but just how do you write down numbers in a digital computer memory? First of all, fun fact, it's actually called digital for those of you who still had Latin in school. Because actually the word for, the Latin word digitus is the word for finger. And digital just comes from the fact because people use their hands to count numbers. But it turns out you don't actually need your 2 hands. That would be a base 10, but you actually only need 2 fingers. And that's the whole idea in writing down numbers in terms of classical bits. So a classical bit is just really a number that can be 0 or 1. And the idea is fundamentally that you write down your number that you want to represent. Here I want to talk about just integer numbers first. You want to write them in this base 2 in the sense that you have a bit that can be 0 and 1, and you do it times 2 to the power 0, times 2 to the power 1, times 2 to the power 2. And with this, of course, you can write down all the numbers if you just have enough bits available. So I show some very simple example here. Let's say you have sort of 4 bits available. Then you can say, okay, the all zeros is the number 0, and then you go to 1, 2, 3, 4, 5, 6, 7. And that's how you do it. Of course, you also want to represent usually positive and negative numbers. So typically what you have in this type of data types is 1 bit that tells you if it's positive or negative. It's called the sign bit. So you typically think about -1 to the power of the first bit. So if it's 0, it's plus. If it's 1, it's minus. So you have the same type of negative numbers in exactly the same way, but then you flip always the first bit to 1. Now, in practically, if you have a computer memory, of course, here you see it would be wasteful to store 2 representations of the number 0. You don't need a +0 and a -0. So typically, one shifts this and one says this is actually -8 instead of -7. You can then go to -8, and then you can go from -8 up to +7. And that's how you write down integers in a classical computer. Right, so one motivation why I tell you to do this is actually, this is not just, I don't want to just do a computer science class, but sometimes if you want to write down in a computer memory some Hamiltonian coupling matrix, let's say you have qubits, and you have one basis state, and you want to couple this base state to another basis state, and you have to find out the index of that one state. then sometimes it is really just flipping one of these classical bits. So sometimes if one does these bitwise operations, one can really speed up tasks that would take a long time if you don't know about this. So this can be actually quite useful in practice. Practical aspect, sort of if we have a modern computer, they usually work with 64-bit architectures, which means your processor processes numbers that like have 64-bit representations in the memory. You can find this if you define a number in your language, which is 1, then you check the type, it's integer 64, meaning it has 64 bits, which means that you can represent numbers only in a limited range, of course, but this range is very, very sufficient. It goes from minus 10 to the 18 to plus 10 to the 18. But it has the funny consequence means that the largest number you can write down is, for example, 2 to the 63 minus 1, right? This is this number down here. And then funny, if you add one of this, right? If you think about bitwise addition, you would go from this, you would go to 1, 0, 0, 0. But then you're over there, and then you have the smallest possible number, right? So if you do plus 1, you're suddenly in the negative range, right? So this would happen if you would go to this regime, but you never need to go there anyway. More importantly, the type of numbers that we really need are what's called floating point numbers. Right? So what we really want to write down is something like h point some fraction, plus minus 1, and then times 10 to some exponent. And I don't want to go into too much detail here. This is really just in case you're interested. So this is the standard way that those numbers are represented. You have usually your sign bit again. Then you have these 11 bits that write down the exponent. This is just the standard integer representation. And then you have all of this fraction. So here I actually wrote down one example of this representation. One thing that is good to know is that, of course, you need only the fraction. So you can forget about storing this 1 because you want to have normalized fractions. So you only have 1 point something. So you don't need to store that 1. So you start only after the dot here. And if I would have something like this here, then the convention is that then this fraction would be 1 plus here this first bit is 0. So it would be 0 times 2 to the minus 1, then there's 2 to the minus 2, sorry, that's a typo, 2 to the minus 3, and so on, and you write down all these fractions for these 52 bits that one has over there. And then for the exponent, one wants to have positive and negative exponents, so typically they are in this biased form, so one does this usual integer thing, but then one subtract half of the sort of 2 to the power 10 from this. So I just give you one example here, how to get to this number. So the number is really represented by this is sort of minus 1 to the power of the sign bit times this fraction and then times 2 to the power of this exponent. And I give this example here. I'm not going to go through it. And by the way, I'm happy to share these PDF notes with you afterwards, so we have to talk about how to do that. So I will skip this, but the most important thing that you have to realize from this is that that's the only important thing from this slide, actually, in a practical point of view, because you have these 52 bits telling you about your fraction. But this means if you have a relative precision of some number, if you want to write down the number 1.0, it's really only defined as 1.0 and then plus minus something like 2 to the minus 53. And this is something like it's on 10 to the minus 16. And that's what's called the double precision. These are also called double precision numbers. And whenever you have numbers smaller than this, numbers that are normalized to 1 and should be smaller than this, then one has a problem. So you see it's completely insane to take something like h bar around because this is something like 10 to the minus 32, I think. Right? So that would not work. So this is a practical tip. And so always what one tries to do is one tries to stay with numbers that are close to 1. Right, so it means if I want to simulate something like a Hamiltonian, here's, for example, a bosonic Hamiltonian where the particles can hop between sides, then it's always a good idea to take one term in your Hamiltonian, like here, for example, this hopping amplitude, and just define it to be 1. And then this sets sort of energies are like a frequency, right? H bar is already 1. So this then sets the time unit. So all the time units are then always given in the inverse energy unit of the number that you choose to be 1. And this is very important to do. Okay, good. So much just about how numbers look in your memory. What's much more important is to think about really the linear algebra of quantum mechanics. Right? So in the end, what we're going to have is just if we keep our state vector exactly in our computer memory, we're going to have our state is going to be represented by a vector with some Hilbert space dimension. I call the Hilbert space dimension always capital D. So I have my state vector, which is a vector of some complex numbers, and this describes the pure state of my system. Right, so now, since we know that we have for our floating point numbers, we have 64 bits, it's important to realize that we have complex numbers, so we actually need two numbers. We need a real part and an imaginary part. So we have in total 128 bits, which are 16 bytes. So if you want to know about how much computer memory you need for a state, it's always going to be Hilbert space dimension times this number d, as long as you stay in this double precision regime. Okay, and this is going to be always the fundamental limit. What you also need, of course, you have to use some operators, for example, the Hamiltonian, or you have to represent some observables, or like a time evolution operator. And that, of course, is going to be represented by a d times d matrix, which is the right-hand side of my Schrödinger equation. One may think this is the memory limit, but it actually turns out you can get away with methods of never writing down your Hamiltonian. So actually the memory limit really comes from this state. I will come back to this later. Okay, but what I want to define is now in a more general way. I talk here about state vector as a quantum concept, but actually it's much more than that. So I want to really talk about a state vector, about any type of vector describing the systems that you have at hand. Right, I have down here some examples. If I now go later to the open system problem, right, I can also just do a linearization of my density matrix. Right? I take my density matrix and I write it just as a snake form. And then I also end up in like a vector representation. This is also a state vector. Or if you have a system of classical particles, let's say you have two classical particles, then you need to describe them with the position of the first particle and the momentum, and the position of the second and the momentum of the last. So you need this phase space of these classical particles. And also those you can put as a vector. So really numerically all of type of problems you want to solve, they're given by some ordinary differential equations, which means that typically the time derivative of my state vector, whatever it may be, is given by a function that can be explicitly time dependent and that can depend on my state. If I go to the Schrödinger equation, luckily this is a super simple equation because there the right-hand side of my equation is just a linear equation, so I can write it as a matrix applied to my vector. And I also only considered here situations where the Hamiltonian is not explicitly time dependent. Right, so this is really actually a simpler way of this more general form. Later we will see that if you go to Gross-Peteevsky equation, which have a nonlinear form, then you need to write down this as a function. Okay, now in this sort of small system quantum mechanics case, people always talk about exact diagonalization. Oh, sorry, I forgot about this slide. So just I have one slide, so just about, again, going back to the question about what can we technically do if we want to keep the state vector fully in an exact form. So here I go again back to my system of qubits or system of two-level systems, where now my Hilbert space dimension was 2 to the power of m. So if I want to use this double precision, I need this to multiply this number by 16, and I get bytes, and in that case I have to put it by 8 bytes. So here I plot the system side as a function of the memory that I need, and of course this is a log scale, so of course this blows up exponentially. But just in practical cases, about if you want to know what you can do on your laptop, not this one here, the one that I destroyed on the beach, then you can realistically hope to get to something like sort of 30 qubits in this type of situation. And again, so in this first lecture and the second lecture, I really want to stay in a limit where I keep all of my quantum state exactly. Of course, what I want to go to at this third lecture is what one can do is one can be much smarter about it and one can kind of use compressed form of your states. And then you can go to much, much, much larger systems because a state has a lot of information and it has a lot of useless information you sometimes don't need. But the first two lectures, I just stay with this exact limit. Okay, so in this field, just fundamentally, when people talk about solving exact quantum dynamics, they typically call it also exact diagonalization, or ED is the typical abbreviation. And this is just simply because if you would do a full diagonalization of your Hamiltonian, then you solve everything that you ever need to know, right? I mean, I think we all know this, but this is just thinking about this more in terms of, right, it's a linear algebra review. So your Hamiltonian is like a Hermitian matrix, right? So it means that it's this Hermitian D times D matrix, so it means it has real eigenvalues. So it means you can find always some unitary matrix, I call it here V. unitary, meaning V dagger V is 1, which means that V dagger is just the inverse of V. And if you apply this matrix to your Hamiltonian from the left side, the V dagger, from the right side, the V, then you get a new matrix, which is a diagonal matrix, which I call here E. Here are the elements of this, and the diagonal elements of this matrix are just the eigenvalues of your system. Right, since this matrix V is unitary, you can write this equation in several ways. So you can multiply V from the left side, then you have H times V is V times E, or you can also just multiply V dagger from the right side, and you can write it in this form. The second form is sort of the way that one is most familiar with in terms of thinking about what eigenstates are, because the second form tells you that this H applied to the columns of this matrix V gives you kind of the eigenvectors multiplied to this column. So what this tells you is that if you look at this, the columns of these matrices that you get, the columns of this unitary transformation matrix, they are actually the eigenstates of your system. Right, if you want to see this, it's good to go to an element-wise picture. So I call the elements of my matrix Hamiltonian matrix small hij. I have this V hij elements, and here I have this diagonal matrix, which is diagonal. And then if I write sort of this matrix multiplication here, is I have index I, index k, I sum over the index k, and I have the index j. So this sum is going to give me the element ij of the matrix that comes out from this multiplication. And then I do the same on the right-hand side, but on the right-hand side I have the diagonal form, so I can get rid of this sum and I just get ej multiplied by vj. And now you see if you define your eigenstate as the column of the matrix, so the first index is the column index, then I see that this fulfills just this eigenvalue equation. Okay, so the columns of this matrix V, they're really sort of the eigencats of my Hamiltonian, in the sense that they really fulfill the time-independent Schrödinger equation. And in the same way, if I look at the rows of this matrix, they're going to be actually the eigenbras, if you like. So they are the Hermitian conjugate of the eigenvectors. That you can simply prove from the conjugate of this equation over there. But on the other hand, you can also bring it in this form. So here, the way that I've written it, it's really, this last form, it's really now that I know that I have my eigenvector stored in this matrix V. So this last form is really the spectral decomposition of my Hamiltonian. Right? So this means if I have my eigenvectors, I can write my Hamiltonian in this new basis of these eigenvectors. Right? That's what it is. It's a basis transformation to the eigenbasis. That's what this matrix V does, which means I have my Hamiltonian written in a diagonal form. I diagonalized it. And of course, if I have it in a diagonal form, I can do anything. In particular, I can do time evolution. So time evolution, you can see that you can do it, because if I take my Schrödinger equation here, if I write down the formal equation, the formal solution of this equation, I have some initial state t equals 0, and then if I want to go to some time t, I have to take e to the minus ith. And that's a matrix exponential, right? So this is a complicated thing. So by the matrix exponential, I mean to write down really the full series of this exponential function and taking minus it h to the power n divided by n factorial. But now if I have my Hamiltonian in this diagonal form, right, then no, I can solve all of this because these eigenstates, they are orthogonal, right? Because my matrix V is unitary, so all of these columns and rows, they're all orthogonal to each other, which means I can write this just by a simple e to the minus the eigenvalue that I have, and then the projection onto the eigenstates. Right, which means if I want to compute what my state is at times psi at times t, and if I have my eigenstates, I can just sum over all of the eigenstates that I have. I can see what's the projection of my initial state to that eigenstate, and then I write this as the new state, and I just add this phase to it. Right, this is how time evolution you can think about. You go into an eigenstate, you add a phase, and then you have this e to the minus itek amplitude of that state at the end of your evolution. And that's exact diagonalization and applying it to time evolution. So I promised to show you a little bit of code. So, and this is really simple to do if you use sort of some modern programming language, in particular this Julia here. So here's just to kind of test the symbol. I'm not going to talk about diagonalization algorithms, because this is really something that's super standard in any language nowadays. So I define, for example, just a random Hamiltonian. This is a function that just create some type of fully random Hamiltonian with 100 times 100 elements. I want it to be a Hermitian matrix, so I just do H is H plus H dagger. This little thing here just is a Hermitian conjugate, super simple. Yeah.
What's the distribution you mean by random Hamiltonian?
It's, in this case, it's a uniform distribution, so all of the elements are between 0 and 1. Right. One can, of course, rand n, and you get normally distributed values. And this is really just to test here. You can put any random Hamiltonian. And then I have like the function here that just gives me the eigenvalues and eigenvectors of this type of matrix. Here, importantly, this E comes out as a vector, so this is not a matrix. But then now, if I do this, I want to convince myself I can just simply test this type of equations that I showed you before. Right, so I have my matrix V. This is this transformation matrix that comes out. I have this E as the eigenvalues. So can I test, for example, these equations? I ask what's the Hamiltonian applied to my matrix. So this is really a matrix multiplication. Then I can subtract of what happens if I apply my matrix V to a diagonal matrix with these eigenvalues. And just here, I just compute the norm of this, and you see it's something like 10 to the minus 13. Right, so this should be 0 because the left-hand side minus the right-hand side should be 0. Here it's 10 to the minus 13, right? So it's actually not 0, but we are still better. I mean, I told you like everything 10 to the minus 16 is the fundamental limit. The reason why we get 10 to the minus 13 is here is just because this numerical algorithm that diagonalizes, it adds some extra noise. It's not perfect. It's also approximate up to a certain limit. And also, I can test this last equation, I get the same, right? So it's an important thing. I want to really, advertise this type of culture to really always test what one gets to understand what is the precision of what one actually has. Okay, but if I have this, now I have my eigenvalues, my eigenvectors, I can just write a few lines of code to evolve a state in time. This is exactly the type of equation that I was writing down before. I want to have my state at the time 0. This is like a vector of 0 elements. I just take some random initial state where I set the first element to 1. And now I want to know what's the state at time psi t. So I just go through all my eigenvectors in the system. I compute the overlap of these eigenvectors with my initial state. I then add the phase to the time I want to go with this energy, and I multiply it with this overlap, and then times the eigenvector, the column. Right. So again, I want to give you the slides. I want to go through that to get a bit of a feeling. I mean, here, for example, I do things very quickly. I write a column of a matrix is, for example, just given by this object here, where I have a double dot, and this just gives me the column K of this matrix. Okay, and that is already enough, these few lines, sort of to do really fully exact time evolution of your state vector. Right? I often see people using sort of toolboxes for all of these things, which is fine, but it's just also really, one can do these things very simply because it's just linear algebra. And I want to encourage you to just think about everything as a linear algebra problem. One can also get matrix exponential directly, usually with an exponential function. However, one has to be careful because sometimes exponential means element-wise. You take all the elements, you take a matrix exponential. This is not what you want. You really want to have the matrix exponentials are really the solution to this Taylor series of the exponential function. Okay, so much about the basics. But now let's do some physics more. So what I want to talk about now is sort of just an example case. I showed you the general concept of state vectors and how to do things. I showed you about the linear problem of quantum, the linear feature of the Schrödinger equation. So let's immediately go something more complex, like let's immediately go to a nonlinear equation. And I think many of you have already seen this Gross-Petersky equation. I will still also just reintroduce it. It's actually quite simple to derive this equation. So the system I want to talk about now is a much bigger system than these few qubit systems that I was talking before. I want to talk about a dilute gas of n ultra-cold bosons which are trapped in some type of potential function. So I write this down here in second quantization. So this is really what I do here is standard BEC theory. So very good, I think, review about this is this Ivan Kastar article on the archive. So there are more details there. So, but I write it in second quantization, so I have type of my free Hamiltonian piece. So this is the non-interacting particles. Come to that later. And then what makes things interesting is this interaction term. And I want to consider really this type of contact interaction, which is a very good approximation for bosonic gases in a Bose-Einstein condensate because they are cold and they are dilute. So all of the interactions one can describe very well with the scattering of the particles, which has this delta potential with some effective strength G. So if I have this delta potential scattering, then my interaction term takes this very simple form. It has 4 field operators at the same position with this effective strength G over 2. So here I have my field operators. I want to talk about bosonic particles. So this psi x dagger it's not a wave function, it's an operator that creates a particle sitting at a position x in your system. And they are bosonic operators, and the fact that they are bosonic operators I put in these bosonic commutation relations. So importantly, I should mention, technically one talks about 3D systems here in general. Here I will just keep it simple, so I just think about it as a one-dimensional system. Also, the way to think about it should be 3D, but I will talk about numerics for one-dimensional systems here. Okay, and then what one can always do is one can now take these field operators and I write them in a different basis. Right? The field operators are operators that destroy and create particles in some type of basis. If I write this psi x, I mean I create it in real space. But in the end, I want to consider a situation where I have some type of external potential. So I have a single body, first quantized Hamiltonian for my particles, which has just this kinetic energy, standard quantum mechanic kinetic energy term, and some type of external potential. And let's say I take this single particle problem and I solved it. Right, for example, I have an harmonic oscillator. I can know exactly my eigenstates of this potential. Or if I have some more complicated potential, I can do some numerical calculations of this. But let's say I have those, and what I can do is now, because they are also a good basis for my single particle problem, I can expand my field operators in this new basis. So I define new field operators, AN, which destroy and create particles in those eigenstates. And then, of course, trivially, if I write my Hamiltonian in this basis, then the free Hamiltonian is, of course, diagonal in this basis. And then only the non-interacting part is non-diagonal. So what I'm interested in here is the time evolution of these field operators. So these are operators, so I have to write down the Heisenberg equation of motion. I have the Heisenberg equation of motion of these operators now with the free part and with this interacting part. The free part is very simple, it's very general. It takes this typical second quantized form where it looks like a Schrödinger equation, but it's actually an operator equation. And the difficult part comes really from the time evolution with these interactions. And that's actually a very complicated term because I have really these 4 operators here sitting in the second term. And it's generally very difficult to solve this unless one does some Bogoliubov approximation where one then effectively writes this as a quadratic Hamiltonian. But let's just see what this time evolution would give me anyway. So I have to compute what is the commutator of my interacting Hamiltonian part with this field operator psi x. So I have this commutator with these 4 operators here written with the coordinate x prime. So I have psi x prime dagger, psi x prime, psi x. And then I can do just some simple commutator magic using these standard resolutions of the commutators here. I'm not going to go through that, but then I see that this part gives me this evolution term with the 3 type of field operators. Right, so my total evolution matrix for my field operator, for my psi x, I can write as minus I times the Hamiltonian, so this is kind of like a standard quantum mechanic part. But then I get this nonlinear part here with G, psi x dagger, psi x, psi x. And this is all an exact evolution equation so far. But then an important approximation, what one does if one goes to this Bose-Einstein condensate physics, is that I say if I make my system very, very cold, it's a bosonic system, I will effectively get a model where I have these single particle states, but really all my particles go into the lowest energy state, and there's only a few particles that may potentially scatter out of the system. But I have a huge number, I have a macroscopic occupation of this lowest state. Now, if I think about this in terms of my field operators that create and destroy particles in this macroscopic state, I can say, okay, if I destroy a particle, if I take one out, it's square root of n0 times some state, and I say the state doesn't change much because I just take one particle out of this big system where I have a humongous number of atoms in it. And I say, okay, n0 is very large, so this is the same as n0 minus 1 and n0 plus 1. So fundamentally, if I make this approximation, the way I can think about it is I just replace my field operators, which are operators here, with a classical number. Right, so what I'm doing here is I take a quantum field theory and I make it a classical theory. So now I have this expansion of my field operators in this basis here, and I say I'm going to neglect all of the higher excited states, and I only take this one state where I have a macroscopic occupation. Yes?
You're essentially taking G to be small?
Well, G in the end has to be small, because if the G gets too large, you're going to get strong interactions that's going to kick your particles out of the condensator. So in the end, one can do this, and in retrospect, one can justify this. Yes. Okay, so what I do is I take only this first term, and in this first term, I replace this field operator with just square root of n. So I define this object, which is technically square root of n times this lowest energy state of my single particle problem. And I define this as psi of x. Looks like a wave function, but it's actually a classical field. And that's the famous Gross-Petersky equation. That's exactly what one does in this type of Bose-Einstein condensate physics most of the time. So this is here, I wrote it again. So really what one does is you take the quantum field theory and you make the field a classical field. And you can justify it in a regime where you have a macroscopic occupation of one of these modes. Okay, so now if I look at my evolution equation up here, which was the equation for this quantum field operator, it becomes an evolution equation for a classical field, right? So I define like my this object that I call the condensate. I define it by this complex number, psi x of t, and it evolves with this equation, where here I had this term psi dagger psi, it just becomes psi squared. Right, so it looks a bit like a Hamiltonian, but it's nonlinear, because if I think about this as if this psi would be like a wave function, then it would be like I apply a Hamiltonian to my wave function, but the Hamiltonian depends again on my state. Right? So it's a nonlinear problem now. People call this the nonlinear Schrödinger equation, but it's a bit sketchy phraseology because, I mean, it's not a Schrödinger equation. It's really an equation for a classical field. It's just, again, if I again put this interaction strength to, say, they're non-interacting particles, then this term goes away. And then I just get the Schrödinger equation for a single particle. It's only that my psi here is actually sort of kind of like a renormalized wave function for a single particle. Right, but in a low order approximation, you have these interactions, and they give rise to this nonlinearity of this classical field. Okay, and that's called the Gross-Petersky equation, and it's an example of sort of a mean field approximation. One can also derive this equation in many different ways. So also, for example, if I forget about second quantization, if I take like many-body wave functions in first quantization, one can also derive this if I say that all the particles are in the same wave function and I make a product state ansatz between these particles. Right? So that's a different way of looking at kind of mean field approximations. It's kind of neglecting any type of entanglement between states. And this is important because I will go back to this later. Okay, I'm sure many of you have actually heard this before. Okay, what I want to talk about is now solving this equation numerically. Okay, so what do we need to do is, okay, the first fundamental problem that we have is that if you look at this field equation here, of course, your psi is defined on a continuous space, right? But on the computer, I have only a discrete memory, right? So I have to discretize my problem. So what I have to do is I have to define kind of a grid. Again, I do everything in 1D, but in 3D, things are really completely equivalent. Now, everything is easily to define on a grid here, but the tricky part is, of course, the kinetic energy that I have of my field. So if I look at this kinetic energy part, so I have my standard quantum mechanical kinetic energy, p squared operator divided by 2m. So this is minus 1 over 2m, and then the second derivative of this wave function. So what I have to do is I have to look at a discrete form of the second derivative of the wave function. Right, so I define my grid. I have a small spacing, let's call it A, like a lattice constant. If I have my box that has a length L, then this A is going to be L divided by M, and I want to consider a limit where this M is very, very large. And then if I look at this discrete form of this type of second derivative that I have here, it means that this operator that I have to write here, because this is going to be an operator that's going to act on my discretized wave function, this operator has this very simple form here. Right? So it has zeros almost everywhere. It just has a -1 on the two off-diagonal elements. And on the diagonal, it technically has this value of -2, but this is just a constant that I can throw away, because for dynamics, this constants in the Hamiltonian, I don't care about. So what I find cool about this, so this is now the matrix that I apply to my discretized wave function. So I define, sorry, I said wave function field. I define my field at discrete positions, 1, 2, up to m. And I act with this matrix, with this prefactor 1 over 2m a squared. I act on this state here. Right, so some interesting thing to point out is that if you look at this matrix, this is really like on a real grid where the particles just hop between neighboring points. Right, so I can also think about this as some hopping. If I define a tunneling amplitude, call it j here, which is 1 over 2m a squared, then this is really just a hopping on a discrete lattice. Right, so it's really completely equivalent to say that your particle moves in a continuous space, you discretize this space, and then you get your kinetic energy means your particle hops between these infinitesimally small elements on my grid. But fundamentally, what I talk about here is really that the simulations I show you here, it's really, you can also think about them as just as a lattice problem, right? In the cold atom physics, we have many lattice problems, like for example, the Bose-Hubbard model that I have over here, written over here. In the Bose-Hubbard model, one traps atoms in these standing waves of light, and then these atoms, they can hop between sides with this amplitude j, and they can interact when they're on the same side. Right? This is really kind of the like real version of this continuous model when I discretize it in real space. So all of the numerics I talk about now here would also apply to sort of the mean field approximation of the Bose-Hubbard model instead, where I can really realize this model also in a real experiment. Okay, so a good thing to think about again is sort of, if you have this model of having particles on this grid, doesn't matter if it's a real grid or if it's this representation of my discretized continuous classical field, we have sort of m particles in our system, and you have to put them on these n sides. Now, you can convince yourself, I'm not going to show the numerical argument, but this is a sort of the Hilbert space dimension is given by this combinatorial expression here. So of course, if you have large numbers, this state vector that you now have can become very huge. But in practice, I can, for example, treat something like 16 particles being on 16 lattice sides, in which case I have sort of something like a 2 to the 8 type state space. That's something that's absolutely doable. Or, of course, I can also go to a limit where I have many, many sites. Like if I take 100 sites and only 5 particles, then also my Hilbert space is kind of relatively large. Of course, all of this is true only as long as I have a conserved number of particles. If I have a situation where I can just remove and add particles to the system, then of course I have to have a much larger Hilbert space, because then I have to have all of the spaces with different particle numbers. Okay, but that's the exact quantum problem. But I told you we are going to this mean field approximation. And now if you think about it, the state vector that we have, like our classical field, right, this dimension of this is only n. If I have n sides, no matter how many particles I put in, I have a state space dimension which is n. Right, so I can now go to a huge system. I can treat like actually sort of billions of lattice sites if you want. So, but of course for doing that we paid this very big price. Well, first of all, we made this very strong approximation. Right, we made this mean field approximation, which means fundamentally we had all particles in the same state. We have no entanglement between them. And of course, the second price we paid, that now our equations are nonlinear. And that's actually a general theme for any type of mean field approximation, is sort of you reduce your state space effectively, but your equations become nonlinear. Okay, but it's fundamentally not a problem to have nonlinear equations. So I don't know how much I'm doing on time. When am I supposed to finish? No.
You're supposed to finish at 12:15.
Okay.
So we have more than half an hour.
Okay, perfect. I think that fits just fine. Because, of course, also nonlinear equations are something that one can easily solve on a computer. Okay, so, and I want to introduce just some numerical class of methods which are called Runge-Kutta methods, and they work for everything. So this is type of your like Swiss Army knife numerical methods for computing dynamics of sort of ordinary differential equations. Okay, just to set the stage of this, so in the most general form, I want to consider now equations where the time derivative of my state vector, whatever this is, depends on a function, with the function depends on time and on the state itself. For example, this is really what I have in my Gross-Petersky equation, right? So this is sort of the function. So I can compute this matrix and then apply this matrix to the psi, and this is my whole function that's sitting on the right-hand side of this equation. And the goal, so this is also called an initial value problem. So the goal is I have a state vector that I know at a time sort of tn. Let's call it, so I have my state vector at a tn time, and I want to know what's the state vector at a little time later. So what I actually have to do, again, classic computer, you have to do like a discretized version of everything. So you have to introduce this type of like little time intervals here. So I want to do a time discretization, and I have my state vector at a time 0, and I want to know what it's at a time 1, and I introduce this time step, which unfortunately in the literature it's also called h, which is very confusing with Planck constant and things like that. But okay, I'll stick to that. And sort of what I want to use is I want to have my numerical approximation of my vector, which I call the vector at this time point n. And this should be a numerical approximation to my exact state vector, which is the y of this I write with this parenthesis. Okay, as I said here, Schrödinger equation would be a linear equation. The function would be just a matrix applied to my state vector. That's the whole function. The matrix obviously being the Hamiltonian multiplied with an imaginary unit. In the Gross-Petersky equation case, this is a nonlinear function. All right, it's named after these two German mathematicians that look very unfriendly in these pictures. Okay. All right, so, but I want to keep to this notation. So the general thing I want to solve this. So what is the first thing that one would come up with? How to solve this? And of course, I can do a Taylor expansion of the thing. Right, so let's start with a Taylor expansion. Let's say I want to know what is my exact state vector at the time tn plus a little step. And if this little step is small, I can write this is the same as the state vector times tn plus h times the first derivative of my state vector plus the quadratic term. Right, but if I make my, my time step super small, then this is quadratic, this is linear, so I can say, okay, let's just neglect everything here. And let's just say, okay, there are some terms of order h squared. And let's just compute this first thing. Right, that would be the lowest order, first order Runge-Kutta method. It's also called explicit Euler method. And what this means is I would approximate my state at the times n plus 1 by the state at times n. I take my little time step, and I multiply it just by this function, so the right-hand side of the equation. If I write sort of this in an intuitive, picturesque form, I would have my exact evolution y of t. And what I would do now, I would take my state at times t, and I just compute the slope at the state t, and from that I project to the state in the future, which I don't know a priori. All right, this is definitely not a good method of using, because first of all, I mean, the error is quite large. You have to use very, very small time steps to actually do this. But what's more fundamentally a problem is that most of the times this actually gives very unstable solutions to your equation. The reason is already in this type of example that I drew here. If you have a real evolution that goes something like this, you see that if you always take the slope at this time here, you always underestimate the exact one. Right? So if you do this many, many, many times, you not only make an error that depends on your step, but you always make the error in the same direction. Right? So which means you would always add up the errors. So effectively, your error is actually going to be much, much larger than just proportional to h squared. So this is really not good, but let's try it anyway, just to see how it actually fails. So let's take, just to test what I'm introduced, a very simple model, the simplest that I can think about. Let's just take a two-level problem. Let's say I have a state vector which only has two elements, which are the amplitudes of a ground state and an excited state. And let's say we have this Rabi problem. So for example, when I drive on resonant this transition in an atom with a laser. So I have a Hamiltonian which has these two off-diagonal elements. And I solve the Schrödinger equation and I start in the ground state of the system. So I define my state vector as this two-element vector. The first one is the amplitude in the ground state, the second one in the excited state. And what I want to compute is just the population in the excited state. Of course, super trivial, I know exactly what it is. It's sine squared t times omega. Right? It's going to be when you solve this thing analytically. Okay, but let's compare it. What we do is if we use this explicit Euler method. So here, this is all the code that you would need to simulate this thing. I have this Rabi frequency, which, as I said before, I define it by 1, which sets my time unit in terms of Rabi frequencies. And then I would have this whole evolution here. I have my initial state. This is a vector where the first one is 1, the other one is 0. And this is just a vector that stores the populations of the excited state. I introduce some time step, which is small, not too small here. And I have some steps, and then I just apply this Runge-Kutta first version every step. Right, so Runge-Kutta first would be just, I take my state vector, and I just take it again, and then I just add h times minus imaginary unit, the Hamiltonian applied to that, return the state vector. So this is what would happen. If you do this, I really encourage you to do it yourself. The exact evolution would, of course, be some Rabi oscillations between the ground state and the excited state. You would just coherently take populations up and down. But if I simulate it with this method, I see that I just keep blowing up over time. This is exactly the fundamental issue. And you can see it very simply from this. What I do in this approximation, I take my state vector at n plus 1, as psi n minus IH Hamiltonian. So if I compute the norm of the state n plus 1, it's always going to increase. Right? It's always going to go with plus h squared. So it's very bad. It's going to be terrible. Someone has to do better than this. And the simplest way to go better is just already the second order method. So here in the second order method, of course, we know all from sort of just approximating integrations. It would be much better if I want to integrate this curve to not take the value at the first or the last point, but to take the one in the middle. Right, so a much better approximation to my state at psi n plus 1 would be the so-called midpoint rule, where in this function on the right-hand side, I enter the value at, times plus 1/2, but also I take sort of the mid value between the state vector here and the state vector there. And if you do that, then I don't do the proof here, but if you just plug in Taylor expansions, you will see that actually you cancel the errors of the second order, and the error that you make in this method is only going to be on the third order. It's a very simple exercise. I encourage you to do it. And now this method would be called an implicit midpoint rule. Right? It's an implicit method, which means that it has the fundamental problem that actually on the right-hand side here, I need a state vector of the future. Right? But that's exactly what I want to compute. But for certain type of problems, it depends now on the function that you have here. You can have situations where you can take this equation then and then you resolve it for yn plus 1. Right? You can have a right-hand side yn plus 1, but you can bring it to the left-hand side and then you still can actually use this implicit method sometimes. But let's assume that in generally one cannot use it. Well, then one way of getting this estimate is just by using some iteration. Right? You notice I can have here an equation where I have yn plus 1 on the right-hand side, on the left-hand side. I can just reinsert the left-hand side on the right-hand side. So let's just do this only one time. So here I've written down this implicit midpoint rule, and what I do is I take this zero-order approximation of yn plus 1 is just yn. Right? So I just insert yn instead of yn plus 1 here, and then I arrive at this thing here. Right? So here I just have 1/2 yn plus yn, so it's just yn. Right? So this is, you can identify again, this is just really the explicit Euler step that I get from this, but now at not the time n, but in time n half. But what I'm going to do is I'm going to use this approximation for my yn plus 1, which is this Euler approximation. And I use this to compute an approximation of yn plus 1 over 2. And let's call this k1. Right, so this gives me this equation there. So this is exactly just this Euler step. So what you can do is you can just compute the value of this in the middle of this interval approximately using this Euler step. This is yn plus h over 2, just this half the time step. And then from that, that's the approximation of this midpoint rule, and that I plug in then again in my second iteration. So I need to evaluate this function 2 times, you see. But if you do this, I get a good approximation to this implicit time step. And that's called like a second order Runge-Kutta method or explicit Runge-Kutta method. And if you do this, you see that things get much, much, much better now already. So I take exactly the same trivial example as before, the same small time step. But now the thing I changed is because I had my Runge-Kutta function, which was the function for the right-hand side of this equation before, and now I use this 2-step procedure where I first compute this value k1, and then I plug this value k1 into this. And then you see that you get really a stable solution of your problem. So it's a much better method, not only because the error is going to be of order h to the power of 3, but also because it gives a much more stable solution. Stable doesn't mean it's stable for all of the problems, but for this problem, for example, it is stable. So here's, we can quantify this main problem, so I can compare, for example, the difference from this excited state population with the exact solution as a function of time. I look at this error and I see in this explicit Euler, the error keeps growing in the same direction. If I use this explicit midpoint rule, then I also get an error, but you see sometimes it's positive, sometimes it's negative. It also keeps growing over time, but sometimes you add a little bit of the norm of your state vector, sometimes you remove it. So it's a much, much better thing to use. Okay, I still don't really encourage you to use this because there's, of course, higher order methods around too. And so here I just put this is the standard 5 equations that you use to implement this so-called fourth order Runge-Kutta method. And this is really sort of the one that everybody uses when they talk about the Runge-Kutta method because it's really simple to actually implement. It's just really these 5 lines of code. And it has a lot of advantages. It has the error being very small. So fourth order means that the error goes like time step to the power of 5. So you can make relatively high time steps. And it's what I want to emphasize, it really pays off. If you think about this in terms of numerical, how much it costs to simulate things, it really pays off to go to this high order method because I can quantify the cost that I have by how many times I have to evaluate this function. Right? That's where all of the thing is going to be. It's going to be a matrix multiplication. It's going to be the expensive part. And here I have to do it 4 times. So in the first order method, I have to do it 1 time. In the second order method, twice. Here I have to do it 4 times. But you do it only 4 times more, but your error just goes as the power, right? So your error is now h to the power of 5. So it really pays off to go to high order. One should really go to as high order as possible. So one may ask, okay, why doesn't one go further? Well, of course, in practice, you want to make some plots about the function of time. And there, this fourth order method is really kind of a sweet spot because typically one has situations where one has 100 steps and you want to make like a plot, you want to have 100 points showing your evolution, right? So you want to have the state at this time anyway. And therefore, sort of some time step, like if you go to times, which are typically 10, something like a time step 0.1 is the nice thing. And if you take this time to 0.1, then this error is small enough that actually you get away with it. And that's why this method is so popular. It's also very stable. Okay, I don't do the proof here. If you want to prove that this is really fourth order with Taylor expansions, good luck. I recommend using some linear algebra numerics. One can understand this method again in kind of this diagrammatic picture. So it's kind of first getting an estimate from the Euler step in the middle here, then kind of refining the slope here from the state that one got, k1 here. But then one gets even a better estimate by refining it again at the midpoint, putting this k2 in here, and then one gets sort of takes this estimation to the last point, and then you kind of see, okay, I mean, this k2 and k3, they are the 2 best approximations to their slope, actually. So one takes this kind of average between them with these numbers. but I'm not going to derive it. All right, good. So again, just showing how well this thing is doing. First of all, I want to again show that it's really simple to code these things yourself. No need to use any external toolboxes or anything. So this is how like the function would look like this for this time step for our problem. So in this problem, it takes a Hamiltonian. This can be now any Hamiltonian. I showed the examples for this two-level system, but it can really be any Hamiltonian. I have my state vector and I have the time step that I put in. I need half the time step, so let's just redefine it to not recompute it all the time. And I need this evolution matrix, this minus imaginary part times the Hamiltonian. And then you see, for example, I compute the K1. It's just this Hamiltonian applied to the state vector. The K2 is just now this the Hamiltonian applied to this state vector over here, where here I have these vectors. This is just a pointwise addition of these vectors. And I go through this here, and it's just a few lines, and then I give back the vector. And if you do this, if you plug in your Hamiltonian, your vector, you're going to get this approximation after a time step h. So again, for our simple problem, you see that this is working like a charm. You see, first of all, that the errors that you're getting, they're very small. They're now on the order of 10 to the minus 7. And on top of that, they also are varying in sign, so it's a very stable method. Okay, so one thing again to just propagate some good numerical practices, one should always really just sanity check of what one is doing. So if I write this type of functions that I showed you here in the slides, do they actually do what I expect they do? So I can take my simple model, I can take a particular time. I like to take the time here 3 pi over 2, because there I know that my sine squared function should be 1. And now I compute the error that I get from my numerical integration minus the exact value exactly at this point. I choose this where the exact one should be 1, so I don't have to renormalize this error, because one should look at, of course, normalized errors. And then I can do this. I can just try the simulations. I run it with many different time steps, and I just compare these different methods here, and I see how my error is actually scaling. And then I see if I do this first order method, so this is a double logarithmic scale. So small time steps are over there, and this is logarithmic. So you want to, smaller time steps you go down here, larger time steps over there. And I see from my first order methods, if I make my time step smaller, it goes down very quickly, the error that I have. It actually goes down linear in h, because this line here is just some random function that goes linear. My double logarithmic scale is always great to look for some power laws. And I see I get here a linear law from this error when I go to small time steps. If I take my second order method, it goes h to the power 3 as it should. And if I take my fourth order method, it goes as to the power h to the 5 as it also should. Right? The sanity check, our method really works. It really makes the error relatively small. There are some funny things happening over there, which you can already barely see, unfortunately. But you see that here suddenly it goes down and then it starts to fluctuate. And of course, you should know what's happening over there. It's 10 to the minus 15, so this is where you hit this machine precision. Right? All of your numbers that you have in your memory are only valid up to number 1 plus minus 10 to the minus 16. So here your numerical code is showing some random noise that's coming from your CPU. So never trust anything down there. The other interesting thing to point out is here we had this first order method, so we would have expected that the error is h squared, but it's actually h to the power 1. So why is this? Well, it's because it's unstable, right? Because I always added my errors in the same way. So effectively, if I simulate for longer times, because I always had the error in the same direction, actually the error goes as linear in h and not squared. So that's really a terrible idea to use this explicit Euler scheme. All right. So now here's just, before showing some nice movies, I told you I want to apply this to this Gross-Petersky equation that I introduced earlier. So here's how I would write this thing in a code version. I have my function which applies this fourth order Ringekutter to my Gross-Petersky state vector, not state vector, the classical field. So I have this field psi. I have sort of this free part, which is like a Hamiltonian. I just apply it, so I give this as an option. And I just give this interaction strength g and my time step. And then what you can do is you can just define, really, that's what one should do. One should define the function, which is the right-hand side of my equation. Right? All what this function here does, it takes this discretized vector psi, and it applies the right-hand side of this equation. Right? So first you see there's a part where I have this Hamiltonian 1. This is this part applied to my vector here. This is this first part. And then I get this nonlinearity where I first have to compute at my particular point. So this is really taking the point-wise values of my state vector, and I take absolute value squared. And then I point-wise multiply it to psi. So this is really psi squared multiplied with psi, with the prefactor of the interaction strength. And if I have this, this is the right-hand side of my equation. I just do these Runge-Kutta lines with the right-hand side with this function. And that's how you would implement this. Okay, so with that, I'm sort of done with really the conceptual part for today before showing some movies. So do you have any particular questions so far? Okay, let's look at some movies then. All right, I said I want to solve this Gross-Petersky equation, so I want to do some fun stuff with it. So I take this equation, again, I have to renormalize my units somehow. I really like to think about this dynamics of this hopping on a grid. So what I define here as units, I define my effective hopping constant, which depends, of course, of the mass of the particles. Right? The more heavy my particles are, the slower they will hop. And then I have this lattice constant, of course, I want to go to large A, but I define this as being 1. I do this Runge-Kutta force method. I have, this is H, this is like the time step in my simulation, which I choose relatively small. And I just take 1001 grid points, which is really not a lot. I mean, you can really go up to 1 billion if you like. But I just want to show some very simple, quick physics. And importantly, one thing that one wants to do, usually I apply periodic boundary conditions over there, which means in my hopping matrix for my kinetic energy, when I arrive at this last site, I hop again to the first site. So I have one very far off diagonal element in this matrix representing this kinetic energy. Okay, so what I want to start off, super simple. Just let's see that if we can get sort of standard quantum mechanics back, I want to turn off the interactions. So initially, I say, okay, there's no interactions between the particles, which makes my equation completely equivalent to a standard single particle Schrödinger equation. Only describes many non-interacting particles, but this is absolutely the same thing. And I want to start initially by compute an initial state of the system, so I want to prepare a wave packet. The way I do this, very pragmatic, I just add, for example, initially some type of harmonic oscillator potential to it, and I ask what's the ground state of this, right? I could also just write down the wave function of this, but I want to compute it as the lowest energy of this ground state. I didn't tell you how to compute ground states from this equation. I will come back to this later, but actually it's a very nice trick. If you have a method that evolves your state in time, you can also always compute the ground state. All you have to do is you have to evolve it in negative imaginary time and keep your state renormalized. I will come back to this later, but that's what I use here. So just trust me for now. And this is what I get. So I have here the plot. I plot this classical field, which in this case is really the wave function. On my grid of 1,000 particles, I have my trap around 0. So this is the wave function that I get, and it's going to be a Gaussian wave packet, as one would expect. So this is a standard wave packet. So how do I evolve this? I want to make the system a little bit more exciting. So I take a situation where I kick the system in one direction. Right? This is like I apply an operator that adds this field gradient to it. Right? This is really, if you go to do a Fourier transform of your wave function, and you look at this operator, what it does, of course, it just takes your distribution that you have in momentum space, and it just displaces it by a certain amount. And I can do this type of kick. I have this kind of kick strength, which one say I have in this Ka, this is this imaginary lattice units that I have. Let's say I put it 0.2, and then I want to know what's happened. Let's see if this works. And you see a wave packet does exactly what a quantum mechanical wave packet does. First of all, you saw the periodic boundaries in actions, but because this is on a ring, so it was, let's see if I can run it again. Oh. Right, so it just goes to the other side, and you do two things. I mean, on the one hand, your wave packet starts to move, But on the other hand, it also gets broader. Right? This is in standard quantum mechanics, your wave packet is going to diffuse. And that's the two effects that you see here. Here, if you notice, I always plot the norm of the state, right, just to convince myself that I have no big error in my system. And you see, of course, that the norm is not exactly one. I'm making some error here on some last digits, which is the numerical error that I do. But this is by far large enough that we can trust these results. So next step, I can also take the same one. I can kick it a bit stronger. Right now, it actually goes faster. It goes around several times, and it also just diffuses a little bit less in the system. Nothing too exciting here. Okay, but now I want to know, okay, what is now the thing, what's happened if I turn on this interaction between the particles? So now I take this interaction, I take it like 5 times of this hopping constant here. So I now my psi is really not the wave function of these non-interacting particles anymore, but now it really is this classical field that describes my Bose-Einstein condensate. And first I do the same thing, I compute the ground state in the system here, and you see that it has a kind of different shape compared to a Gaussian. Right? In particular, you see it has this type of, it's much, much broader. The physics behind it is simply you have interacting, right? It's a repulsive interaction. So the particles don't want to be close to each other, they want to repel each other. Right? So you modify your ground state classical field in this case. And in particular, I encourage you to look this up. If you talk about Bose-Einstein condensate, so here we are in the so-called Thomas Fermi limit, where the interaction is much stronger than this kinetic energy. And if one is in this Thomas Fermi limit, one can get analytical results for this shape of this classical field. And the easy thing is just, what you can do is it's kind of a copy of what your trap is doing the other way around. So the shape that the trap has down here, it gets copied, it gets inverted and copied. And this is this Thomas Fermi limit, and this is exactly the same effect that you see happening here. You get this broadened shape of your Bose-Einstein condensate, which has this shape. Okay, so let's see how this thing evolves now with the interaction. I apply my very gentle kick to the system, and nothing too exciting happens. It's the same thing as before. You diffuse, and so on the one hand you move in the system, on the other hand you diffuse. You see that because of the interactions you diffuse much, much stronger, but still through all of this evolution that we have here, so all of this evolution, we still keep this kind of broad shape, right? So I'm not showing this here technically, but this means that really your kind of Bose-Einstein condensate stays intact, right? It just changes the parameters, but it just gets more broadened. Here is some funny aspect I want to point out. So you hear here some little wiggles happening. You can wonder, what is this? Why is this there? Any ideas? Well, it's not real. I mean, you see, here you are now in a limit where your wave function is sort of the same, the whole length of the world that I consider. Right, so here I reach a finite size problem. Right, because you see I'm broad enough so that it goes almost over the whole system. So I get some artifacts from the fact that I'm in this finite box. And it really tells me I should make my box much larger. Okay, and now the last thing I want to know, I could do the same. I do a kick a little bit stronger. I go in from 0.2 pi to 0.4 pi. And let's see what happens. And this thing tilts over and then hell breaks loose. Right, so this is like a wave. You can go out there on the beach. That would be great to observe again. You see that your thing is, it's first like tilting over and then it just falls apart. This destroys your BEC. And this is, in effect, very well known. It's already quite interesting complex physics. It's known as dynamical instability. It's if you have a BEC and if you kick a BEC, either if you kick it strong enough above a certain threshold, it's going to fall apart, or if you make the interactions go large enough above a certain threshold. And with this simple method, we can already see this type of physics here. There's only one problem with this. It's fundamentally wrong. Right? Because what I completely neglected is I did this mean field approximation, and I talk about a one-dimensional system in this case. Right? One-dimensional systems you can treat exactly as you learned this morning. We'll also come to numerical ways how you can exactly treat large one-dimensional systems later in the lecture 3. The problem is just that this mean field approximation is really not working if you have a one-dimensional system. So we could treat a very large system, but we made a very strong approximation And you have to, of course, be careful when you make these strong approximations, and we will come back to this in the third lecture. Okay, but that's it for today. I think just on time, so let me just do a review of what I tried to tell you today. So we talked a little bit about how to present actual numbers as bits in your classical computer memory. And I just introduced this kind of linear algebra picture where we had state vectors, where importantly the state vectors are really not limited to Schrödinger equation evolution, a really very general concept for any type of system. We just write it as a vector, and then if you have a linear problem like the Hamiltonian dynamics, then it's just a matrix vector multiplication that happens all the time. If you have this, then we discussed if you have a Hamiltonian, you can just do a full diagonalization of this Hamiltonian, and with this you can technically solve everything. It's not the most efficient way to solve things, but one can really solve everything. But of course, not all problems are linear problems. In classical physics, it's full of nonlinear problems, but also in quantum mechanics, you can get nonlinear problems by making classical approximations. As an example of this here, I showed the Gross-Petersky equation, which comes from the full quantum field theory for Bose-Einstein condensate, and making this field a classical object, neglecting entanglement between the particles, you arrive at this nonlinear equation. If one has these nonlinear equations, still, I mean, for both linear and nonlinear, one can always use these Runge-Kutta methods that I have introduced. And they are really methods that come from a very simple consideration of the Taylor expansion of your problem, and you just want to do multiple evaluations of the right-hand side of your function to write your state vector at a later time in such a way that you really cancel the errors in your Taylor expansion. And the most popular thing there is this fourth order method, which has a very small error and it's stable. I hope I got a little bit across the idea that it's really important to think about stability of your algorithms, because you can have a very low error, but your problem still blows up. But this is a very good general Swiss Army knife tool that one can use. And then I applied this whole machinery, Gross-Petersky, in like a one-dimensional Gross-Petersky equation, which is something I should have never done because Gross-Petersky doesn't work in 1D, but I did it anyway. And I discussed it a little bit about this dynamical instability that happens in the situation. And really all of this I did here, all of these plots, they are really a few lines of code. So I really encourage you, I really like this culture of understanding physics by really trying to simulate it, because it tells you a lot about what's actually going on in the dynamics. And this is a theme that I will also keep in the next lectures. Okay, and I think with this we can all go to lunch, I think.